Okay, so far we've discovered that it takes energy to raise the temperature of something. Another thing that involves energy is chemical reactions. Any chemical reaction involves some sort of change in energy. These changes in energy, when they occur in the form of heat, are given the term heat of reaction. Oh, whoops, I was thinking ahead of myself. All chemical reactions involve a change in energy. One way reactants gain or lose energy is through heat. A special term, and this is a term that's going to be very important to you next semester and can get a little bit confusing, even though it shouldn't, because really it's very simple, and that is when the heat of a reaction occurs at a constant pressure, the change in heat is called the change in enthalpy. Enthalpy, heat. Enthalpy, heat. Essentially the same thing, just at a constant pressure. Matter of fact, enthalpy is so closely related to heat, it's given the symbol capital H with a triangle for change, or a delta for change. So change in enthalpy. Let's take a look at a fairly easy to relate to reaction in one of my favorites. One thing I love to do is I love to react hydrogen and oxygen. The reaction of hydrogen and oxygen to form water also produces a great deal of heat, and it's very visible when that heat is released. Matter of fact, let's take a look. I do this nearly every semester for my face-to-face class. It's one of my favorite reactions. I've only caught myself on fire doing it twice. I have a balloon right here, and that balloon is filled with hydrogen gas. I'm going to burst it and expose it to oxygen. In addition, I'm providing a little bit of flame to get the party started. And all right, thank you for humoring one of my favorite demonstrations there. So we could clearly see that heat was being produced by that reaction. And where do we write things that are produced in a chemical reaction? As a product. There are actually three ways to denote changes in heat or heat of reaction, just in terms of writing them. The first way is to write the heat or the quantity of heat lost or gained in the chemical reaction like it's a reactant or like it's a product. In this reaction, heat was a product, so we wrote it over here on the right-hand side of the equation. This way of writing things is very common in the field of biochemistry. Another way of writing the heat of reaction is to write the chemical formula for the reaction like you normally would, then have a semicolon, Q equals, and then a negative sign if heat is released or heat is a product. Because your system or your chemicals are actually losing heat, right? Energy can't be created or destroyed. So if a reaction is producing heat, that means our chemicals are losing it. So our system is losing it, which is why we have that negative sign there. And yet another way of writing it, if your reaction takes place at a constant pressure, instead of writing Q for heat, you can write delta H for enthalpy. Couple things to note. This quantity of heat given here, here, and here is in stoichiometric ratio to the reactants in the chemical equation. What do I mean by that? Well, you're already happy with saying that if I react 2 moles of hydrogen gas, then I can produce 2 moles of water. Well, that heat now joins the party. So I can say if I react 2 moles of hydrogen, I can produce 572 kilojoules of energy. In other words, writing heat in the form of a chemical reaction gives me a conversion factor between number of moles and energy. And we're going to have some fun with that stoichiometric relationship here in a few seconds. I'm probably getting ahead of myself. All right, now let's look at somebody's good example gone way too far. Back in the dark ages of chemistry, some chemistry professor came up with the world's best graph to help their students understand heats of reaction. However, somewhere along the line, it went from being an instructional tool to being something actually tested. Therefore, we have to spend some time going over energy diagrams. All energy diagrams, which is this picture you see here, and I'm going to change my floaty color here. All energy diagrams have energy along this axis, and this is the energy inside the chemicals, or, well, this is the energy on this axis, and then progress of reaction or time on this axis. All energy diagrams follow a similar pattern. You have a flat area to start off with, and that's the amount of energy, that's the amount of potential energy stored inside the reactants. Then you have a hump once the reaction gets started, and then you have another flat area down here, and that flat area is the energy of the products. If we were to apply it to our reaction that we just witnessed here, we'd have our 2 moles we'd have our 2 moles of hydrogen and our 1 mole of oxygen over here represented by this line. Over here represented by this line, we'd have our 2 moles of water. The difference in height between those two lines is equal to the heat of reaction. In this case, we know from the previous slide that it was 572 kilojoules. All right, so we now know why we have these two lines, and we know that the difference between them is equal to the heat of reaction released. But what about this area here? What about this little hump? When I burst the balloon, in order to get the reaction to occur, what did I do? I used a match, right? That match provided what's known as activation energy. Activation energy is the energy required to start a reaction. And we'll actually redefine it later, but it's the amount of energy required to get a reaction going in order to start a reaction. We're familiar with this concept, right? Everybody in here has lit a match. Now we know that matches give off energy and produce them. We can feel the heat coming off of them. But in order to get the reaction started and get that match burning, what do we have to do? We strike it, right? We're adding kinetic energy to it to get the reaction started. We're adding activation energy. So in all reaction diagrams, you'll see this little hump here representing the energy of activation. And I have probably gotten way ahead of where I wanted to be. Real quickly, the heat of reaction is the amount of heat absorbed or released during a reaction. It is the difference between the energy required to break bonds in the reactants and form bonds in the products. In order to make our water from our hydrogen and our oxygen, what do we have to do? Well, we have our hydrogens single bonded to each other, and we have our oxygens double bonded to each other. Well, we have to break that single bond, we have to break that double bond. That requires an input of energy, right? You break up with somebody, it requires energy. You go eat the chunky monkey, the rocky road, you calorie load because you're burning so much energy up because you're breaking up. Forming bonds releases energy, right? If you really like somebody and you finally hook up with them, then you feel that big release of energy, right? That tension goes away, the moment's finally arrived, you have admitted you liked each other, right? Forming bonds releases energy. The difference in the energy it takes to break the bonds and the energy released from forming new ones is the heat of reaction, or the change in energy that accompanies the reaction. Reactions can be divided into two big categories: exothermic reactions and endothermic reactions. An exothermic reaction is a reaction that releases energy. In order for it to release energy, since energy can't be created or destroyed, the energy of the reactants has to be greater than the energy of the products. And because we always subtract final state, we always subtract the initial state from the final. Remember, final minus initial, and the final is lower than the initial. We can see that on our diagram. Because of that, we wind up with a negative value. Exothermic reactions will always have an energy diagram where the reactants are higher than the products. When we write an exothermic reaction, we'll either see energy as a product, or we'll see the Q or change in enthalpy value as a negative value, signifying that heat has been released. All right, everybody needs to write down Daredevil. Everybody write down Daredevil. Endothermic reactions are the opposite of exothermic reactions. Endothermic reactions are reactions an input of energy or heat. For an endothermic reaction, because you're adding energy to the reactants, the products will have higher energy inside their bonds than the reactants. So we'll see an upward motion to the hill. And in our energy diagram, the products will have higher energy than the reactants for an endothermic reaction because heat is being absorbed. Because heat is being absorbed, it's written on the reactant side, and because we're adding it to the products, it's given as positive. This is what we call a slide put in there to help you study for tests. Activation energy, we already covered, is the amount of energy required to break the bonds between the atoms of the reactants. And that's really all we're going to cover at this point. We've already covered where it is on the reaction diagram. Notice for an exothermic reaction, it's this way. For an for an endothermic reaction, it's much taller. It's always the difference between the top of the hump and the reactants. Top of the hump and the reactants. Identify each of the following reactions as exothermic or endothermic. Okay, I look at this here and I see that I have energy as a product, so that means it's exothermic. For number 2, I see it as a reactant, so it's endothermic. Quick note about endothermic reactions. I instinctively wrote it in blue. Why? Because endothermic reactions feel cold to the touch. If they require heat in order to happen, endothermic reactions, where do you think they get that heat from, since it can't be created or destroyed? They get it from the surroundings. And if we're touching a beaker where an endothermic reaction is occurring, we're part of those surroundings, so it's going to feel cold to the touch. If you've ever got a cold pack, where you snap the little capsule inside and it turns the bag into ice, that's an example of an endothermic reaction. Here we see heat as a product, so that would be another example of a exothermic reaction for number 3. Chemistry's easy, life is hard. It's a lot easier than if your name is Nova. Everybody write down Nova. Here's another one. The enthalpy of a solution for ammonium nitrate is 27.7 kilojoules per mole, making the reaction is endothermic or exothermic. How do we figure this out? Sign, sign, everywhere a sign. Right? What's the sign on 25.7? It's positive. And whenever we see positive, we know it has to be endothermic. Chemistry's easy, life is hard. All right, let's take a look at solving some problems using heat of reaction. If 15 grams of nitrogen monoxide are produced according to the following reaction, how many kilojoules were absorbed? Well, I have no idea how to work this, but I know that they only gave me one number to start off with in the problem. 15 grams of nitrogen oxide. I know my next step is going to involve getting rid of nitrogen monoxide, and the only thing I ever know how to do with grams is go to moles. So that's exactly what I'm going to do. We're in a little bit of a crunch for time, so I'm going to take some liberties, and I'm going to call 14 the atomic mass of nitrogen 14 and the atomic mass of oxygen 16, so that we have a mass of 30 grams. So we've gotten rid of grams of nitrogen monoxide. We've gone to moles of nitrogen monoxide using molar mass as a conversion factor. I have moles of nitrogen monoxide. I don't want moles of nitrogen monoxide. What do I know about moles of nitrogen monoxide that would do me good? Well, I know I want kilojoules. Do I know a relationship between kilojoules and number of moles? Yes. A chemical equation gives you the relationship between any of the substances in it and the change in enthalpy, or the change in heat. So I know, thanks to that chemical equation, that 2 moles of nitrogen monoxide are produced, and they require 180 kilojoules. So I know that 2 moles of nitrogen monoxide is equivalent to 180 kilojoules. So I've gotten rid of moles of nitrogen monoxide, and I've gone to kilojoules using my chemical reaction. So it's just like that moles of A, grams of A, the grams of A, moles of B equation, except instead of going to moles of B, we're going to kilojoules. So I'm going to multiply everything on top, divide through by everything on the bottom. 15 divided by 30 times 180, divide by 2, and I get 45 kilojoules. Chemistry's easy, life is hard. It also works the other way. How many grams of oxygen are reacted if I'm getting tired and can't talk, if 306 kilojoules were released from the following reaction? We have, oh, come on, my stylus is wearing out, 306 kilojoules. We have kilojoules, we want to get rid of them. The only thing we know about kilojoules is what this chemical reaction tells me. It tells me the relationship between kilojoules and oxygen. That 213 kilojoules is equivalent to 2 moles of oxygen. So I've gotten rid of kilojoules. I now have moles of oxygen. I don't want moles of oxygen. They're asking for grams of oxygen. I know that 1 mole of oxygen is 32 grams of oxygen, thanks to my handy-dandy periodic table. Hey, grams of oxygen is the unit I'm looking for, so I must be done. I multiply everything on top, divide through by everything on the bottom, and I get 306 times 2 divided by 213 times 32. That gives me 91.9 grams of oxygen. Is that right? That doesn't feel right. Just a second. Let me do that again. 306 times 2 divided by 213 times 32. That's what I get. All right, let's work one more. It would not hurt for you to pause me at this point and try it on your own. If 20 grams of rust react with excess aluminum, what is the change in enthalpy of the system? Well, we've got one number to start with, 20.0 grams of rust. I don't want grams of rust, so I know the first thing I'm going to do is I'm going to get rid of them. The only thing I ever know about grams is molar mass. So I go over to my periodic table. I've got 2 irons at 55.845 plus 3 oxygens at 15.9994 gives me 159.68 and change. I have moles of iron, 3 oxide. I don't want moles of iron 3 oxide, I want energy. According to my chemical equation, it's a 1 to 801 mole of my rust is equal to 852 kilojoules. Multiply everything on top, divide through by everything on the bottom. And that gives me a negative 106.7 or a negative 107 kilojoules. Okay. Couple things about the wording here. In this problem, they asked, what is the change in enthalpy of the system? Since they did ask for what is the change, I definitely want to include that negative sign. It would be wrong if you didn't. If they had rephrased that question to ask how much heat was released, then that negative sign wouldn't be required. As a matter of fact, Mastering Chemistry might even count it wrong if you put it, because they're asking for how much heat was released. By using the word released, they would have told you the negative sign is present. So watch your wording when you work these problems. Here, they use the word change, meaning they're not telling you the direction. Come on, stop that. Since they're not telling the direction of the heat flow, you have to include that negative so that people know what the direction of the heat flow is. If they had said released, then they would have told you the directions with the word, and they'd be looking for the quantity or the absolute value. All right, now let's do something really cool. Let's roll what we know about specific heat and what we know about heats of reactions into one big, glorious, massive problem that will totally raise the roof off this party. In order to do that, we have to do the science of calorimetry, something I happen to have a master's in. Using another way to think of calorimetry, or what we're going to do, is simply using 2 or 3 simple equations at the same time. Hey, I have 3 different titles for this section. I feel like the old Bullwinkle show. Anybody watch Bullwinkle? But I digress. We must look for a moose and squirrel. Couple terms we need to define right off the bat is the universe. Everything in existence is the universe. The system, what we're interested in studying. The surroundings, everything that is not part of our system. Internal energy, the sum of all the energies for the particles that make up our system. In other words, the total energy of our system. Important to note, your textbook uses a capital letter E, and it'll often go E sub I for internal energy. Most other textbooks you encounter actually use U for internal energy. Why they use U for internal energy instead of the universe, I don't know. If we look at my carefully drawn drawing here, you can tell that's something I drew here. I have a piece of iron, and I want to know about the piece of iron. So my iron would be my system. I dunked my hot iron in cold water. This cold water is in contact with my system, so that makes it part of the surroundings. And technically the beaker would be part of the surroundings, and so would the air, so would the sun, right? But the surroundings that are immediately in contact with my iron to exchange energy would be that water. This identification of my surroundings and my system is going to be very important to the science of calorimetry. The first law of thermodynamics is not enforced by Speedball, but it could be. Everybody write down Speedball. Forgotten Marvel characters for 100 Alex. The first law of thermodynamics states that energy cannot be created nor destroyed. It can only be converted from one form to another. This has several implications. First, since energy can't be created or destroyed, that means that the total energy of the universe has to be constant. All the energy that there ever was and all the energy that ever will be is already in existence. That means that the change in the energy of the universe is always going to be equal to 0. Real important. And since the universe is equal to the energy of the system plus the energy of the surroundings, and the change in the universe and the change in the energy of the universe is 0, that must mean that the change in the energy of the system plus the change in the energy of the surroundings also has to be equal to 0. This simple equation summarizes all of the science of calorimetry. It's an equation we're going to make use of several times in this chapter. Oh, here's my writings of what was on the other slide. Calorimetry is the science of measuring heat flow. You study calorimetry using a calorimeter. It's an instrument used to measure energy flowing into a system. Really, a calorimeter is usually a big insulated vessel used to separate your system and the system's immediate surroundings from the rest of the known universe. Remember, insulators don't absorb a lot of heat, and they don't allow a lot of heat to pass through them. Let's take a look at the type of problem we'd be working in terms of calorimetry. An aqueous silver ion reacts with aqueous chloride ion to yield white precipitates of solid silver chloride. When 10 milliliters of 1 molar silver nitrate is added to 10 milliliters of 1 molar sodium chloride, and the solution is at 25 degrees Celsius in a calorimeter, a white precipitate of silver chloride forms, and the temperature of the aqueous solution increases to 32.6 degrees Celsius. Assuming the specific heat of the aqueous mixture is 4.184 joules per gram per degree Celsius, and that the density of the mixture is 1 gram per milliliter, and that the calorimeter doesn't absorb any energy, calculate the change in enthalpy in kilojoules for this reaction. The key to working anything in calorimetry is identifying your system and your surroundings. Whenever you see a chemical reaction, you immediately want to declare that your system. That's my system. That's not my lion. It's two. All right. You immediately identify that as your system. Well, what's this reaction taking place in? This reaction is taking place in water, or it's taking place in a solution. In this case, my solution is my surroundings. Okay, so that means that since the change in the energy of the universe is equal to 0, then the heat flow of my system plus the heat flow of my surroundings is equal to 0. So that means that the heat released from my reaction plus the heat absorbed by my solution has to be equal to 0. Do we know anything else about any of these? Well, we know that our solution is changing temperature. Right? We see temperature increasing, and whenever we see a temperature changing, that's a big clue to what? That's a big clue that we have to use our specific heat. So we know for our heat of solution, at least, we're going to use our specific heat formula. Do we have everything we need to in order to solve that specific heat formula? Do we have a mass of our solution? And that's where things get really complicated in problems like this, and where reading everything kind of becomes super important. If we look at our problem, they're telling us that we're mixing 10 milliliters and 10 milliliters. They're then telling us that we've got a density of 1 gram per milliliter. So 10 plus 10 is 20. And 1 gram per milliliter is 20 grams. So we do have a mass. Not only that, they gave us the specific heat of the solution here as 4.184. So now we can say we've got 20 grams. We have a specific heat of 4.184. They told us that the final temperature was 32.6 and that the initial temperature was 25. So now we can solve for our heat of reaction. So I punch this into my calculator, and I have 20 times 4.184 times the quantity, 32.6 minus 25, closed quantity equals our variables on the same side of the equation as the number we need to solve for it, right? So we need to subtract from both sides. Since we subtract it from both sides, that winds up making the heat flow of our reaction a negative 635.97 joules. I will tell you right now, if you're taking a multiple choice question, that will be choice A. Every single time, that will almost be choice A. That is not the right answer, however. That is the amount of heat released when we reacted the quantities we reacted. This is the amount of heat released based on what we reacted. However, we did not react 1 mole. Why is it important that we note that we didn't react 1 mole? Well, remember, this chemical equation, and we're being asked to solve for the change in enthalpy for it. The change in enthalpy for a chemical reaction is based on those coefficients. In other words, it's going to be based on us reacting 1 mole of silver and 1 mole of chloride. We didn't react 1 mole. We reacted much less than it. So we have to figure out how much of each one did we react. So what we kind of need to do here is we kind of need to make a clean sweep here, as a matter of fact. Let's see if I can't clean up my workspace a little bit here. Bear with me, I know this makes stimulating viewing here, but it's worth it in the long run. Okay. We didn't react 1 mole. Instead, we reacted 10 milliliters of a 1 molar solution of silver and 10 milliliters of a 1 molar solution of sodium chloride. Well, 10 milliliters, place milliliters where they cancel out, 10 to the negative third liters, times molar. Remember, molar means 1 liter, and then the number of moles on top. So that's 10 to the negative 2 moles of silver we reacted, and we reacted the same quantities of sodium, so we also have 10 to the negative second moles of sodium chloride. or chloride ion. It's a 1-to-1 reagent, 1-to-1 ratio here. So, and since we have the same amount, we don't have to worry about a limiting reagent, which makes life really, really nice. So we only reacted 10 to the negative second moles of silver. Another way to think of it is 10 to the negative second moles of silver ion yielded 636 joules of energy. We need it per 1 mole. What do we do? Very formally, your change in enthalpy has units of joules per mole or kilojoules per mole. With that in mind, looking at those units, what would you guess we do? We're going to take the amount we actually reacted and divide it into our yield. We produced negative 636 joules when we reacted 10 to the negative second moles of silver. That gives us 6.36 times 10 to the 4th joules per mole. And if we want to make it nice and clean, we would go ahead and convert to kilojoules. All right, let me give you a little bit of a flow chart here to solve a calorimetry problem. I'm not talking here, I'm concentrating. Identify the system and the surrounding. Use 0 equals Q plus the system plus the surrounding to solve for the Q of system. Change Q system to units of kilojoules per mole by dividing by the number of moles of the limiting reagent. That's how you should solve your calorimetry problems. Beep.